Hello YouTube and anyone else who's interested in my research. Right now I'm going to go over one of my ideas called map search. The idea is to turn the exception unwind table into a hash map, into a lookup table. Well, not a lookup table, but a hash map. So here's the main idea. Let's kind of just go over exceptions in general and how they work. So the very basic way that they operate is that when you call throw, you capture your CPU state, you get your program counter, and from there, you then need to figure out how to unwind your functions. Now, in order to do that, there are a couple of blocks of memory that you have to consider. One of them is the exception index, and one of them is called the exception table. The exception index has an entry for every single function, where the structure of this is an array, where the first element in the object of the entry object is the function address. The second entry is either the unwind information immediately, if it's a reasonably small function to unwind and doesn't have anything like a throw or a catch inside of it. Otherwise, it'll be a pointer to a structure that includes all of your unwind information. The position of each entry in the exception index corresponds to the location of your functions. For example, if the first function in your binary is foo, and the next one's bar, the next one's baz, then the first entry in your exception index will be foo, then bar, then baz. They are positionally, they correspond positionally to each function. In here you can see kind of the idea. So function address, instruction address, and then I have a little bit of breakdown of how these things split up. These other parts here aren't super important. What we're really looking at is the exception index and how we go about searching it. Currently, we search it using binary search. It's a O-log of n operation. It's relatively good, as you would need your entire code base, the number of functions you have, to double before you'd end up doing another iteration in the binary search. So it scales reasonably nicely. The problem is that it's still a lot of effort to do for the CPU to do the binary search, all the calculations it needs to perform. It would be nice if there was an O of 1 solution. Now, I've talked about other O of 1 solutions, like turning your code into basically a lookup table, turning the exception index into a lookup table by expanding and padding out certain functions so they all align to 64-byte or 128-byte blocks. These are great. Here's an issue, though. That increases your code size dramatically. Is there a way to get around this? Well, there's one idea, which is map search. So let's take a look at what I've kind of done here. So what I've done is I have a function start address. Actually, let me go over here to the data. Here is every single function in Firefox. I took the Firefox debug version, I dumped all its symbols, and then I saved them here. Now, I basically deleted all symbols that were less than 32 bytes in size, or sorry, not symbols, but the function symbols that are less than 32 bytes in size. My guess is that they probably aren't throwing anything or doing anything clever. Most of these are probably not doing anything either. Note that Firefox does not use exceptions, so this is not really relevant. I just needed some source of data that I could play with as if it was using exceptions. I think this is good enough, just to see how the code sizes and objects vary and how many you end up having to deal with when you have a large project. So you got a lot of like things that do, I think it's like brush stuff, like for rendering stuff and all that. It's all good stuff. A lot of these are 32 in size. This could definitely be turned into a lookup table directly because there are so many of these in here. And then we can go a little further on, and then you can see how they kind of grow in size. And then I've sorted them by smallest to largest. Yep, and you have some really large function down here, which is nearly 200. It's greater than 250K, and then it starts to slump down. So here are all the symbols and all the functions in Firefox. Now, my idea is if you were to sort all of your functions, you could have a mapping for each program counter to a specific function without that function being arbitrarily complex. So here's kind of how this would look. It's kind of hard because the dots are so small and I have like 5,000 of them here, but I'm actually going to take this, I'm going to lower it a bit to just 1,000. Let's just make it 100. And you can kind of see. So the x-axis in this case is the program counter location, and the y-axis is the entry. So the idea here is I want to have some function where I can put in a program counter and get back out what the corresponding uh, entry table index is. So y is our entry index, x is our program counter, and then we just use a curve fit and we can get it. Now let's move this guy back up to, what was it, 5,000? There we go. Cool. So here's the cool thing about this. If you were to sort all your functions and lay them out in this way, you can effectively estimate where the entry is going to be. So for example, let's say, this one's really with all the small functions, so this one's going to be a little weird. This section here, which is at the other side of the functions, the largest functions, is going to be a little weird too. They're going to be a little off because they're kind of, they have the, on one side here, we have so many functions that effectively have the same size. And that can have some issues in the beginning where it starts to deviate away when you get further away. And then on the larger side, you have a very few very large functions. I can actually show you what that looks like. So what happens is you start off small as you increase your program counter going forward, and then eventually, because those functions are getting longer, it starts to bend more significantly to the right, and that's why you get this curving thing. It starts to curve over versus being a straight line. Now here's the cool thing. So I can take this value here, put it into this little estimator here, take the equation from the curve fit, throw in my program counter, and get the corresponding entry that it should be. For example, let's put in 0 here. I get 12. That's actually kind of far away, but these are some small functions. Let's go over here to this number here. This would be 142. I'm going to line that up. And we get 149. Now, here's the idea with map search. We just need to get a approximate, get relatively close within 10 to 20 entries, because iterating left or right in ARM instructions usually only takes 2 instructions and only takes about 2 cycles. You might need an additional cycle for whatever you need to do to convert your current program counter to a relative offset value. That's another complicated thing about the spec. I'm not going to go into it here. But for the most part, it only takes about 2, let's say 3, even 4 cycles. Now, to kind of give an idea of how many cycles it would take to do this normally with binary search, I've done some estimations with the Cortex M4 floating point turned off, because you don't really need floating point for that operation. It's just a lot of shifts and addition and subtraction. So we're going to go to Wolfram Alpha, and then I know the number of functions is down here, 249212 log 2. And I know it takes around about 14 cycles per iteration we have to do. So this gives us the number of iterations we have to do to break down the structure down to do the search down to where we need to go. And it's how many instructions or cycles it takes to actually for each one of these iterations. So we're going to calculate that, and we get around about, 250. Cool, 251, because it rounds up there. Cool, so 251 cycles. Now here, if I put this number in, we're probably gonna, if we have a floating point unit enabled, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 operations we have to do here. Maybe another one for rounding, so it's 11. So we have 11. From what I gather, the FPU is really efficient, so it can do a lot of these multiplications and additions in a single cycle. So let's just say that we end up having around about, I'm going to throw out there 15 cycles. Okay. Once we get to this point here, we see that we are at 149. We have 1, 2, 3, 4, 5, 6. 6 spots to move over. We're going to check this value. We're then going to see, hey, is it greater than, less than the function we're looking for? Oh, it's greater than? All right, let's move backwards then, until eventually we hit the thing that we're looking for, which is 142. So let's go. 1, 2, 3, 4, 5, 6, 7, 8. So we have 15 plus 8, 15 cycles for the math, plus 8 times, I'm going to just go with 3 cycles. And we have 39. So that's much smaller than 250. Let's just do a little, how much percent? divided by 250. I'm just going to go with that, and then multiply it by 100 to get it to percentage. How much percentage? Actually, I think I just do percent here. I think it'll give me the percentage. Okay, I don't know if that's how that works. I'll just keep it like that. So yeah, 15.6%. That's really good reduction, in my opinion. And some of these guesses can be really good. So if I scroll down here a bit, I'm just going to go here, going to punch that right in. It should be 2, line that up. It should be 2166. 2167. All I have to do is move to the left one. So what you can see here is that if we can estimate where our entries are, we can then very quickly get right to the entry, maybe do some movement left or right, and then find our value that we're looking for. I have done this for multiple other sections. So this is from 0 to 5,000. So the first function down to the 5,000th function. Then we have 100,000 to 105. I want to do something kind of in the middle to see how that works. You can already see this guy doing its thing. If I find this in here, you can see that the actual entry is 42.97. This is 42.99. That's really close. I can get you another one. Let's move this guy up a bit. Let's go here. We're looking for 1884. 1888. So we're really close. We're only 4 entries away. And this one I think works really well even when you're close. So let's do 280. -5. So one cool thing is that if we ever get negative numbers, we can just seal them up to 0. And then, what was that, 280? That's only 2. If I maybe put in this right here, what do we get? 6. So we're off by about 7. Not that bad though, still. So that's pretty good. Still less than how many we were off last time. Then you can even get to the end. And this is where, it can get a little bit more funky because these functions can get rather large at the end here. But we can then, I don't know, take this guy here, move that one in. And I'm looking for, where are we at? 108, and I got 105. That's really good. We can move down a little bit. Go right here. I want 1865, 1868. Beautiful. All right, and then we can go all the way down here, and then we can go like something like this, and that should be 4976, 4988. So this one's a bit far off. This one's a bit off, so it's going to be a little more pricey around here. We could split up this section into more smaller sections in order to make this work. So there are options here. Now, one thing you may consider is, okay, well, how do we store these coefficients? Well, we'll probably have a matrix to hold all these coefficients. But let's kind of take the number of overall functions, which is this number, is the one that you saw down here. Just the number of functions, and if you want to just kind of prove it, it's this number here, or this number here, or not this number here, but like it's this entry here minus the 1 that we have here for the header. So we take that, we divide it by 5,000. I did this by chunks of groups of 5,000 functions. I need 4 bytes for each 32-bit floating point number, and I'm going to need at least 4 coefficients because the way that I did this is I did a curve fit with 1, 2, 3, 4 coefficients. And with that, the cost to us is about 797.5 bytes. So that's the amount of additional metadata you need in order to curve fit all of your functions. I think relative to how large this application is, which I think it's about 100 megabytes. I think paying an additional 800 bytes is nothing really. Yeah, so that's the idea. Basically chunk up your code and then do a curve fit. If you're wondering why the program counter starts at 0 for each one of these different sections, I found that Google Sheets basically doesn't work really well when you don't start from the origin. So if you start from the origin, do a curve fit there, it's really accurate. So yeah, that's pretty much it. That is map search, and I'll be doing hopefully a talk and some papers and other things like that later on. But until I get to that point, yeah, just keep up on the libhouse stuff, keep up with what we're working on, and I'll eventually have talks about this in the future. All right, bye.